Okay, I've got a pendulum, and holding it by a knot, going to time it for 30 seconds. 1, 2, 4, 5, 6, 8, 10, and count by twos. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, got 49. And I actually did this before and messed up the video, but that's exactly what I got the last time I counted it for 30 seconds. Now I'm going to bring the knot over to the center of the washer, and then I'm going to take a paper clip and locate the point on the string where the pendulum will be swinging at half the length. Now there's a little bit of thread overlapping there that could affect the results, but we're going to time this for 30 seconds. Ready? 1. Messed up. It's going to have to wait just a few seconds till the second hand lines up at a place that I can read reliably. Are we ready? 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66. Okay, I got 66. That's not what I expected to get, but you know, when we do data, we do this as honestly as possible. So the length is L. The length here is 1/2 L. And now I'm going to make sure everything's lined up correctly. And looking at the knot, I'm not sure this didn't slip just a little. But, okay. I'm doing this off camera. Matter of fact, I'm going to pause for a second. Okay, that's folded in half about as well as I can do it, as precisely as I think I can do it. I'm going to count to 30 seconds. Ready? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 8, 9, 40. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now I was counting a little differently this time. Before I was counting, this time I was counting full cycles, a full cycle being from here over to here and back. Previously I was counting half cycles, so that the number of whole cycles here was 98. That's at 1/4 the length. Now I'm going to just off camera repeat something real quickly. I really don't believe that. I think I might have counted, looks like I might have been, well, no, maybe my count was okay. We'll go with it. Okay, now you can verify my 30-second counts because, of course, you have you're playing this on a video player that almost certainly has a count in seconds, or shows you the seconds, minutes and seconds of the time from the beginning of the video, so that you could verify these. That one was closer to 72. There are uncertainties in my counts. I'm first of all counting with this clock, which doesn't have really precise markings, and the clock is off to the side. I'm reading it from an angle, so I don't have really good parallax. Also, there are other little things about the way the pendulum is swinging. My fingernail causes the pendulum swing to be a little shorter when it gets over here. So there's some uncertainties. Nevertheless, here are some data. Now, I'm going to graph these data. I'm going to graph the count versus the length. Okay? So that means count is going to go on this axis, and length is going to go on this axis. The first length was L, so I'm just going to put L here, and then I'm going to cut that in half. So there's 1/2 L, and I'm going to cut that in half, so there's 1/4 L. My counts were 49 for the big length L up to 98. So I can put a scale up here that goes up to 100. I can divide that 100 in half and divide that 50 there in half and this 50 and get 75 here, 50 here, 25 here. They're going to be little errors. So this seems quite a bit shorter than this, so I don't have really good scale. But anyhow, 49 is going to be pretty close to 50, just a little less, so I can come over here, straight over from 50, hopefully parallel to the axis, and I get a point. 72 is going to be a little less than 75, maybe about here, and that's just going to come over to this point and then down to the 1/2 L point, and then 98 is very close to 100, and that's the point that I'm going to have with my 1/4 L. Now I can draw a smooth curve through these points. Okay, so I'm going to just draw a smooth curve that goes here and here and seems to follow that trend. Now, on the smooth curve, okay, I don't want to pick one of my actual data points, but I'm just going to pick a point, let's say, right here. And I'm going to estimate. Well, I'm just going to sketch the length. There's a scale here, but I'm not going to bother with the numbers. Now I want to double this. So I'm going to go here and here. This doubles. Okay? Then I want to double this length. Okay, that doubles and comes out to here. Now, I'm going to draw a yellow segment here, yellow segment here, and a yellow segment here. Now I did this off camera, so you didn't have to watch the whole thing. You could easily draw this. To this first yellow line, I drew an arrow from the x-axis, and then to the second yellow line and the third yellow line. Remember what those yellow lines mean. The first one is the count that we would expect at whatever the length is corresponding to this mark on the x-axis. Second is the count that we would expect according to this mark. The third is the count that we would expect according to this mark. If I look at these arrows, I see that this one appears to be about 80% the length of this one. And this one appears to be about 70% the length of this one. Now you might make different estimates. Actually, I think this one's probably a little over 80. This one's probably pretty close to 70. Might even be just a little less than 70. Now the question is, do we have a power function? Well, if we have a power function, and if it's drawn with complete accuracy, which this isn't, it's a hand-drawn sketch, and there's some anomalies here, then in doubling the length, we should get the same thing each time. We should get the same factor each time. That's a property of a power function. And that doesn't appear to be the case here, but remember that this is a hand-drawn graph. Among other things, this y-axis doesn't make really that great of a right angle with this x-axis. So there's some little anomalies, and this 25% up here is bigger than this 25%, or even a little bit is smaller than this 25%, and even a little smaller than this one, probably about the same here, so that the scale of the axis isn't done perfectly, and the horizontal scale is probably done a little better, but it isn't perfect either. Well, from this hand sketch graph, and using these points, we can't confirm for sure that this is a power function, but if it is, if this graph really does represent a power function, then remember that the y factor for a power function, well, then the y factor here, when we double x, is about 0.75. And remember that the y factor for y equals x to the p is 2 to the p. So we have the equation 2 to the p equals 0.75. And we want to know what the power p might be. Solving the equation, we get p is approximately equal to negative 0.42. In other words, if you do this in your calculator, raise 2 to the negative 0.42 power, you're going to get 0.75. You could easily enough use trial and error, trying different values of p until you got one to which you can raise 2 and get 0.75. And you can easily, in just a couple of minutes or less, get that to within two significant figures, and you'll probably agree with the negative 0.42 as opposed to negative 0.41 or negative 0.43. Now remember, this is based on a flawed graph and hand sketch, so we don't really take that negative 0.42 too awfully seriously, but we know now that if this really is governed by a power function, if the count versus length is governed by a power function, then the power is going to be something not too much different than negative 0.42. Now from this, we might want to conclude that this thing is y equals x to the p with p equal negative 0.42, so that y, the count, should be the length raised to the negative 0.42 power. However, we don't have a scale. We do have a scale on the y, but we haven't scaled the x-axis, except in terms of the length of the pendulum. And that's not a standard unit of length. If we want to scale this in terms of, let's say, centimeters, well, the length of that pendulum is probably around 30 centimeters, so 1 centimeter would be over here pretty close to the origin. Or if we wanted to do it in meters, 1 meter would be out here somewhere on the length scale. We could do it in inches. An inch would be maybe about here on the x-axis. The scale that we use for our x-axis determines what we would have to multiply by x to the p in order to have a good model. Now, I'm not going to actually do that here. We'll do that later. But we then say that the model would be y equals ax to the negative 0.42, where a is some number as yet to be determined. And of course, we could rewrite that, since y is the count and x is the length, as count equals a times the length to the negative 0.42 power. Once more, a is a quantity that we would determine once we have a scale on each of the two axes. Now, a better graph would imply a factor of about 0.7. In other words, when x doubles, y changes by a factor of about 0.7. And 2 to the p equals 0.7 implies that p is about negative 0.5, so that your model would be count equals a times length raised to the negative 0.5 power. And we see the model right here. Put a big prominent circle around it. Now you can repeat the count. Remember, you have the screen. You can make a more accurate count and get a more accurate graph with good lined paper and so forth, and come up with a much better model, and maybe confirm the negative 0.5, maybe not.